Hi, today's class is about International Data Encryption Algorithm, IDEA. Okay, now this is also a block cipher and it is a symmetric key block cipher. So there is only one key for both encryption and decryption. Okay, now this was designed because differential and linear cryptanalysis is not possible on IDEA. Okay, so here also we have got 64-bit blocks being encrypted or decrypted, and the key size is 128 bits. Initially, this was designed in 1991, and it was used for secure encryption over digital media. Okay, for applications like communication, financial transactions, electronic voting, etc. Okay, and simple mathematical operations, a number of sequential simple mathematical operations were used to convert the plain text to the ciphertext. Okay, we're going to look at all these things in detail, and we will be doing one example. Even though, the actual idea is 64 bits, I'll be showing you an example with 16 bits. Okay, and then the same thing is repeated, like the similar process is used on 64 bits. We'll be looking at it in detail later. Okay, the advantage over here is that the cipher is highly secure and it is resistant to many attacks, including the linear and differential cryptanalysis. Okay, one of the other strengths, even DES had this, it could be implemented both in software as well as in hardware. Okay, and because simple mathematical operations are being used, it was relatively faster and required small amounts of memory and processing power. So it was a very popular choice for a long period of time until AES came to be in a circulation. So even though now IDEA has been replaced with AES, there are several legacy systems, earlier systems which used IDEA, still using IDEA. Okay, now we're going to go into some details. I told you earlier, the key size for IDEA is 128 bits and the block size is 64 bits. Okay, so it encrypts a 64-bit plain text into 64-bit ciphertext. Okay, now to do this, initially the plain text, the 64-bit plain text is divided into 4 sub-blocks and each block is 16 bits. Okay, so 16 into 4 is 64 bits. Then there are a series of identical 8 rounds. Okay, and in each round, the same transformations are going to be done. Only the input and the output will be different. Very similar to DES, where there are 16 rounds, but here there are 8 rounds. Okay, and the output of one transformation is called is given to the next round as input. Okay. Now, after all this is done, to get the actual cipher, there is another round which is done, which is called a half round, which is done to get the actual cipher. Okay, so it is similar to the 16-bit plain text block. The cipher block is also the exact same size. Okay, so we're going to look in detail. Even the half round has got 16-bit plain text and 16-bit ciphertext. Okay, a block cipher, we already know this. We know the Feistel structure. So we know that block ciphers normally operates in round blocks with part of the encryption key and with known as the round key applied to each round, followed by other mathematical operations. After a certain number of rounds, like in IDEA it is 8, in DES it was 16, the ciphertext for that block is then generated. Here the ciphertext is generated by having another round called the half round. Okay, whereas in DES, it was simply, interchanging the left side and the right side of the cipher. Okay, now what happens in each round is what we're going to look. The idea, which is International Data Encryption Algorithm, derives most of its security from multiple interleaved mathematical operations. And what are these operations? Modular addition, modular multiplication, and bitwise exclusive OR. Okay, now I'm assuming you know what is modular addition and what is modular multiplication. Okay, so for example, if I am saying 10 plus 8 mod 16, 10 plus 8 mod 16. Okay, what is 10 plus 8? It is 18. But we have got mod 16. So we cannot have any number that is more than 16. So we will be doing after 16, again we'll be counting 1, 2. Okay, so 10 plus 8 mod 16. What will be the output? Ten plus 8 mod, sorry, mod 16 is equal to 2. Okay, so 10 plus 8 will be in bracket. Wait, let me just show you here. Okay, this is what I mean. 10 plus 8 mod 16. Okay, so actually the output will be 18. But because we have mod 16 over here, we cannot have any value greater than 16. So to get 18 after 16, again 17 is counted as 1, and 18 is counted as 2. Okay, so this will not be, 18 will not be the right answer here. The answer will be 2. Okay. Okay, so this is what I mean. Now, what about if I'm saying 10 into 8 mod 16? Okay, so actually 10 into 8 is 80. Okay, so what would the answer be for 10 into 8? That is modular multiplication. What would be the answer? It will be equal to 0. Why? Because 80 divided by 16 is equal to 5. It is exactly 5. So there is no remainder. So it is 0. Okay. So here the answer is 0. Okay. This is how we are going to do modular addition and modular multiplication is going to be done. If there is one remainder after doing a division by 16, then the answer will be that there's no decimal points. Answer will be 1. For 2 remainder, it will be 2, etc. Okay, so please brush up on your modular addition and modular brush up on your modular addition and modular multiplication. Okay, and then we have the bitwise exclusive, or I hope you know that bitwise exclusive, or is simply 2 bits are being bit by bit, we are going to be doing the XOR. Okay, so those are the three operations which is going to be in multiple interleaved: modular addition, modular multiplication, and modular bitwise exclusive OR. Okay, we will be looking at examples soon. Now, how exactly encryption is being done in international data encryption? Okay, so in IDEA, we already saw that 64 bits is being divided into 4 blocks, and then a 128-bit key is going to be divided into 16-bit keys, subblocks. Okay, so there are 6 16-bit key subblocks. We're going to look at how the keys are generated, how the encryption is done. All these things are going to be looked at. So just bear with me. Okay, when 16-bit 6 keys are used, 96 bits have been used. And then the rest of the bits will be used for other things. So we just bear with me, we will be looking at it. Okay, so initially the 64-bit plain text is going to be divided into 4 equal blocks: x1, x2, x3, x4, each 16 bits. Okay, then the 128-bit key is going to be used to generate 16-bit key subblocks for 6 rounds. So Z1, Z2, Z3, Z4, Z5, and Z6 are the sub keys which are going to be used for each round. Then for subsequent output transformation, that means to get the final cipher, the rest of the 4 16-bit key subblocks are going to be used, and total will be the 128. Thus, from a 128-bit key, a total of 52 16-bit subblocks are generated, because remember, for each round we use 6 bits and there are 8 rounds. So 48 keys, sub-keys are required to complete the 8 rounds. And then there is a half round in which another 4 keys, sub-keys are going to be used. So 48 plus 4, 52 16-bit subblocks, keys, sub-keys are generated for the whole encryption. Okay, and in each round, there are 3 algebraic operations: bitwise XOR, modular addition, 2 raised to 16. So 16, 2 raised to 16 modular addition, and 2 raised to 16 plus 1 modular multiplication. So one modular addition is base 16 and the other modular addition is base 17. Okay, now we are going to look at the steps and then we will be looking at an example. Okay, so a complete round, there are 8 rounds. In one round, there are 14 steps. We're going to look at what the steps are. Okay, multiply x1 with z1. For each round, there is z1 to z6. Okay, so the first round is here. Multiply for each round, each 16-bit is going to be multiplied by the 16-bit K1. Okay, so the 64 bits are first divided into x1, x2, x3, x4. First step is x1 modular multiplication with K1. Okay, and remember mod multiplication is with modular 17, and modular addition, which is shown by this box, is done with mod 16. Okay, we're going to look at all that. Now, the first one was multiply x1 with z1. So it's modular multiplication. Then add x2 with z2 and x3 with z3. Those are steps 2 and step 3. And fourth step is again modular multiplication, x4 with z4. So the first 4 keys are used in the first 4 steps. Let's look at this diagram. x1 modular multiplication k1, x2 modular addition k2, x3 modular addition k3, x4 modular multiplication k4. The first 4 steps are done over here. Okay, then the fifth step is bitwise XOR the result of steps 1 and 3. So result of step 1 and 3, and bitwise XOR result of steps 2 and 4. Okay, so we're going to look at the diagram now. The result of these two, step 1 and step 3, are bitwise XORed, that is step 5, and the result of the second step and the fourth step is being bitwise XORed over here. So till here we have got up to step 6. Okay, now we're going to look at step 7. Multiply the result of step 5, that means this bitwise result, with Z5. So again, modular multiplication, the result of 5 is going to be multiplied with Z5, that is the fifth key, sub key. The results of step 6 and 7, so this XOR and this 7 is added. Okay, so we look at that much. So here, this result is being modular multiplied, and that result is being given to the XOR result of to do modular addition. Okay, so up to this is S7. And similar to that, we are seeing multiply the result of step 8, that is this result, with Z6, and then add step 7, the result of multiplying with Z5 and Z6, we add those two. Okay, so look what's happening over here. This XOR result is being multiplied with K5. The result is being given to modular addition of the bitwise XOR operation of the 7th step, and that result and this result and this result is this result is being modular multiplied with K6, and then those two results are being given for modular addition. That is what we saw till now. Then these 4 steps, XOR steps alone, are pending. Okay, so over here, the result of x1 k1 modular multiplication is bitwise XORed with the result of this step. Okay, so look what's happening here. Bitwise XOR the results of step 1 and step 9, bitwise XOR with the result of step 3 and 9. Similarly, bitwise XOR, see, we can see over there 1 and 3 was taken together. So 1 and 3 is being XORed with the result of 9, and 2 and 4 is being XORed with the results of 10. Okay, and that is the whole step. And then finally, there is an interchange before the values. This value is given like this. This is the first 16 bits. There is an interchange in the middle to 16 bits. That is the result of the middle to 16 bits. And the last bit is given directly. And then again, the same process is going to be done 8 times. Okay. So let's see exactly. And here the half round will also be present. Okay. So example. Now to just show you the simplified example, we are using a simplified idea where the input is only 16 bits. Okay. And the 16 bits is divided into 4 bits each. Okay, and the key is 32 bits, right? 1, 2, 3, 4, 5, 6, 7, 8. 32 bits. Okay, So we have plain text is 1001, 1100, 1010, 1100. This is the key 1101, and the final after all the rounds. Here I am showing you only the output of one round. I will need you to do 4.5 rounds, and finally you should get this cipher. Okay, so here I'm going to show you how one round is done, and then you all can do as homework. The rest here, the output is 4.5 rounds. Okay, so 4 rounds and the final round. Okay, now the plain text over here is 16 bits, so we are dividing it into 4-bit pieces. So x1 is 1001, x2 is 1100, x3 is 1010, and x4 is 1100. Okay, there are 6 keys, and the last 2 keys are going to be used for the 0.5 round. Okay, so that we will be looking at later. So the keys K1, this first 4 bits is K1, K2, K3, K4, K5, and K6. So that's shown over here. Now, in these 14 steps, star is for modular multiplication using mod 17, plus is for modular addition using mod 16, and this caps symbol is for bitwise XOR. Okay, so now what we are going to do, the first step was, what was the first step? X1 modular multiplication K1, right? Look at the image, X1 modular multiplication K1. Okay, so that is 1001 modular multiplication 1101. 1001 is 9 and 1101 is 13, and when you multiply it and mod it with 17, you get 15. You can check. Okay, second step was, you can look at the diagram, x2 plus k2. Okay, so we have x2 1100, k2 1100, and both are 12. So modular addition with mod 16. So that will give you the output 8. Okay. Similarly, the next step is x3 modular addition k3. After that, x4 modular multiplication k4. Okay. So do each step, and when you have done each step, finally you have 7, 8, 11, 9. Okay, but you remember that over here, for the next round, there is an interchange in the middle 2 values. So the output over here is 7, 11, 8, 9. And because 12 and 13 will finally be interchanged. And then again, this you should give to the next round. Okay, so after 8 rounds, you will get these values. And then there is a 0.5 round. Remember, there was a final here. For subsequent output transformation also, another 4 16-bit key subblocks are required. Okay, so for the final output to be got, again we need to do a few steps. Okay, now let's look at how the rest of the rounds are being done. Here we are doing a simplified version, so there are only 4.5 rounds. Okay, so the first round we explained in detail. For the first round, we had a key with 4 into 8, of which only this first 4 bits we used. Okay, so the rest 4 bits will be used in the second round. Okay, now you can see a star over here. What does that mean? What it means is that the key is actually 4 into 8. Okay, that is 32 bits. we will do a 6-bit left shift. So these 6 bits will be concatenated over here. Okay. So the next round or the next 8 subkeys will be from this bit onward. 0, 0, 0, 1. See over here, 0, 0, 0, 1, 1, 0, 1, 1. Here 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, and 1, 1, 1, 1. Okay. This is 1, 1, 1, 1. Then 1, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, and 0, 1, 1. So till here, you have the next 8 bits. The next time for the third round, this is the key. So you take 0, 0, 1, 1 to 0, 1, 1, 1 as the 32 bits, and this you will shift 6 times. So you will get 1, 1, 1, 1, 0, 0, 1, 1, etc. up to here. Okay. Again, next time from the K5 of the third round to the K6 of the fourth round, you will take as the key, and it will be shifted 6 bits to give you the next 4 bits. Okay, so you will have 1, 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, and 0, 1, 1, 1. For the half round, you don't require 6 keys, you only require 4. Okay, so this is what is going to be used. And then this, for the 4 rounds, you will simply follow the 14 steps. These 14 steps with the new set of keys and the output that we got over here. So this is x1, x2, x3, x4 for round 2. Okay, and the key will be these keys, K1, K2, K3, K4, K5, K6. Once all the 4 rounds are done, or in the case of normal IDEA, once all the 8 rounds are done, then the last step or the half round is completed in this way. You have got the output from the 4th round, which is another x1, x2, x3, x4. So there the first step is x1 modular multiplication k1, x2 modular addition k2, x3 modular addition k3, and x4 modular multiplication k4. And this is the final output. The final output is simply concatenating all these 4 blocks. So each of them were 4 bits. You will now have 16 bits. Okay. And that is how you get this output ciphertext. So you can check this. And in the case of 64 bits, you will do this for 16-bit subblocks. And with this, IDEA is done. We'll continue in the next class.